Welcome back. Before we proceed further, we need a few elementary, let's say, basic facts from the differential topology. These facts are, I'm sure, you will be able to find in any standard textbook on differential topology. So let me begin, and we'll introduce first a few definitions. So definitions. So suppose f from Rn to Rm is a C1 differentiable map, and x naught belongs to Rn. Then we say that A x naught is a regular point of f if the derivative of f and x naught, which is a linear transformation of Rn to Rm, is surjective. And b x naught is a critical point of f if x naught is not a regular point. Which means the derivative is not surjective. The derivative is not surjective. Of course, okay, so this is our first statement, and maybe let us also notice a couple of other things. So maybe let's make another definition first. Definition. And in this definition, assume that f again from Rn to Rm is a C1 map and maybe like this, put it comma, D is contained in Rn is a set, and y naught belonging to Rm a given point. Is a given point. So then we say that A y naught is a regular is a critical value of the map f restricted to D if and only if there exists a point x naught belonging to D satisfying the property that f of x naught is equal to y naught and x naught is a critical point. It's a critical point. And then we have B. Y naught is a regular value of f of restricted to D, f restricted to D, if and only if it is not a critical value. So now we have this definition, so we can formulate the first important result. This was basically a classical theorem that you can find in any textbook of differential topology. Let's write it down, theorem. And we'll call it Sar's theorem. I formulate this theorem only in the generality that we need here, so you should look into the maybe more, let's say, general formulations of that statement, of this theorem. However, for our purposes, it's enough to have this formulation. So let f from Rn to Rm be a smooth map D contained in Rn a compact set then the set of all regular values of f restricted to D is open and dense in Rm. Is open and dense in Rm. So as I said, I refer to the differential topology textbook to prove it. So another one, the simple consequence of this theorem, let's call it like this, also a theorem, and we formulate it like that. Suppose f from Rn to Rm is a C infinitely differentiable map. Put it like this: omega contained in Rn and open bounded set such that f of x is different than 0 for all x's belonging to the boundary of omega, and assume that 0 is belonging to Rn is a regular value of f restricted to omega closure. Then we have two possibilities. Then either, I can put it first on A, f minus 1 of 0 intersection omega is empty, or B, f minus 1 of 0 intersection of omega is non-empty, so put it like this, M is n minus m dimensional compact oriented submanifold of omega. So this is a kind of a very nice property of the regular values, that the inverse images of regular values are submanifolds. So of course put here corollary. If 0 is a regular value of a smooth map, maybe put it like this, C infinity map f from 0, maybe like this, f restricted to omega bar f from Rn to Rn and omega contained in Rn open bounded set, right, such that maybe like this, maybe and f omega is admissible, then clearly f minus 1 of 0 intersection with omega is a compact manifold of dimension n minus n, 0, so that means it is a finite set. So that means it is a finite set. It is a finite set. So of course we'll be paying attention to this property. Maybe we need one more, and before we proceed further with the properties of the degree, we need one more, so let's put it like this, theorem, that's also important. Regular approximation theorem. Let f omega be an admissible pair and maybe specified here. F is from Rn to Rn, and then you have here omega is open bounded set of Rn. Of course, all the maps that we are talking about are continuous. 10. For every epsilon there exists, and I put it like this, F0 or F naught omega belonging to M, so this is another admissible pair. Pay attention that omega is the same, so that means F0 is approximation, and we'll be considering it as an approximation on F of F, such that we have the following conditions satisfied. Conditions, so first A, that F0 is smooth, and just simply C infinity map, and 0 is a regular value of F0 on omega bar, and the B is that for every x belonging to omega, put here bar, and here we have the norm of f of x minus the norm of x naught is smaller than epsilon. Smaller than epsilon. Let's do the proof, because here is nothing difficult. So why to avoid the proof? First, notice that by Weierstrass theorem there exists a C infinity map. Call this map F1 from Rn to Rn, satisfying the property that for every x belonging to omega bar, f of x minus f1 of x is smaller than epsilon over 2. We can assume actually that maybe like this, maybe actually that in order to take care of admissibility, so such that for every f, so we have here f of x minus f1 of x, so we can assume actually that this is smaller than minimum, and put here epsilon over 2, and here I put here again minimum x belongs to omega bar, and this will be f of x, and we know this condition will assure that f1 is also, this is exactly so. So f1 omega is admissible. So this will help us to get this property. So once we have it, we can now use the Sart's theorem. 10 by Sart's theorem. There exists, because the set of the regular values of F1 is dense and open. Dense is here the property that we are using. So there exists an Y node belonging to Rm such that Y node is a regular value of F1, and we also assume that Y naught is smaller, and again I put here epsilon over 2 in order to have approximation, appropriate approximation, but I still want to assure, I want to assure that this approximation that I'm constructing is admissible. So I'll put it like this, minimum, again, minimum, and I put it epsilon over 2, and this will be for the purpose of having everything admissible. So now this will be F1 of X, so sufficiently small. You know. So then we know, so the map, and this map that I'm constructing is F0 from Rn to Rn, given by F0 of X is equal F1 of, sorry, nicely, F1 of X minus Y0 has the properties. So the first one, 0 is a regular value of F0 restricted to omega bar. Why? Because Y0 is a regular value of F1, so that's exactly the property that guarantees that there are no critical points of F0 in omega. And the second one is B, that we have for every X belonging to omega bar, we have here that F1 of X minus zero of X is smaller than epsilon over 2. That's what we needed, and hence so you are getting here that F of X minus F0 of X is smaller than Fx minus F1 of X, and then you go down and write it down, plus F1 of X minus F0 of X, so that means it's smaller than epsilon over 2 plus epsilon over 2 is equal to epsilon. So yes, we are getting an approximation. And finally C, we have here that F0 omega belongs to M, and that's by the condition, by the continuity, let's say, by the fact that this value here that we chose here, you see, is satisfying this property. So it cannot reach the boundary, it's separated from boundary. Okay, so this is basically the end. So we prove it, so we have here this property. So maybe I'm just checking if we have enough space to formulate one more result. So we have here that the approximation is satisfied. Maybe just remark, I put here like this, remark, and then we'll switch to another page. Remark. Notice that the above argument in the theorem, in the last theorem, so how in the regular approximation, in the regular approximation theorem, is also valid if we assume that f is going not from Rn but from Rn to Rn, and for us maybe it's important to indicate n could be larger equal than m, and all the statements that we made actually will still be valid. So we have here that the regular approximation theorem can be proved in a more general case. So like you just simply so it means it is true not only for admissible pairs f of omega, but also for admissible homotopies. For admissible homotopies. And we will refer to this remark later. So let's go to the next lemma that we will need before we prove the result, main result of this lecture, namely the analytic formula for the degree, for the computations of the degree. So maybe put it here, the following lemma. So this is lemma. Suppose f from Rn to Rn is a smooth map. We write something like C infinity map. X naught belongs to Rn such that maybe and X naught belongs to Rn, a regular point of f such that f of x naught is equal to 0. 10. Maybe put it like this. Defined the homotopy. Define the homotopy H, and this will be from 0, 1 times R n to Rn, and this will be the definition. So H of Tx will be equal, this will be 1 minus T f of x plus, and this will be T df of x naught, and this will be x minus x naught for x Tx belonging to 0, 1 times Rn. 10, the statement is the following. 10. There exists a delta larger than 0, such that for every t belonging to the 0, 1, and for every x belonging to the boundary of the delta ball at x naught, we have here that h of t x is larger than 0. In other words, the homotopy H is B delta 0 admissible. The homotopy is B is admissible. Very good. So let's do the proof. So assume for the contradiction that the statement is not true, that this statement star is not true. And that would, what would it mean? That means in particular that for every delta, take delta 1 over n, a natural number, there exists a point Tn and Xn where such that it belongs to the 0, 1 times Rn, satisfying the properties that first of all Tn is in the 0, 1 and norm of x minus x naught minus norm of xn is equal 1 over n. That means it's in the boundary. That means simply here that xn belongs to the, maybe write it under. That simply means that xn belongs to the boundary of b delta of x naught. So that would contradict the statement. And of course here we are getting here h of Tn xn is equal to 0. So notice, because by compactness, zero, 1, just simply by passing to a subsequence, we can assume without loss of generality that this Tn is actually convergent. So let's do it. Tn converges here. Very good. Good. 10 we have. So let me write it down. So what do I have? I have here 0 is equal of h of Tn xn is equal, so what do I have here? 1 minus of Tn, and then I have here f of xn, and here plus Tn, and here I have here df, and this one is x naught minus xn. So let's use the differentiability of f. So that means simply I can continue, I can write 1 minus Tn and use the differentiability. So what do I write? I write here down that this is equal f of xn. And now we have here, of course, we have here something which can be written like f write it down like this. F of x naught, didn't write it down. F of x naught is 0, yes. So we have that one. You see, we have that one. So I can use it here. So that's nothing, that's 0. And then I put here again minus, and I add the new thing. So this will be df of x naught minus xn. Close it. And then, of course, because I have here minus, I will put here plus. And then we have here 1 minus tn. And here we have here, and then you have here df of x naught minus xn, and then still we have here tn df of x naught minus xn, and you see something cancels. This and this cancels. So I can rewrite it down and rewrite it down and write it down. First of all, notice that we call it like this in the calculus. This is called the remainder, because you have differentiability, so you have here remainder. Let's denote it. This will be like xn, and that will be like x naught. So what we know what means the remainder, that like this is going faster to 0 than x and approaches x naught. So we'll use it. So what do I get here? We are getting here that this is equal to 1 minus tn, put here the remainder, xn x naught plus tn df of x naught minus xn. Sorry. Not tn. df x naught minus xn, like that. Wow! Since, let's formulate it. Since, by the definition of derivative, limit as x goes to x naught, we have here r xn x naught divided by the norm of xn minus x naught is equal to 0. We obtain that, put it like this, limit as x goes to x naught, and I put here like this, df of x naught minus xn divided by x naught minus xn, which is equal to 1 minus t0, and this will be limit of r of x and x naught divided by xn minus xn is equal to 0, since we have that d, and I introduce here a new notation, vn up goes to 0 as n goes to infinity, for vn being exactly this particular vector. So this is x naught minus, I think I made a, of course I made a mistake. How can you notice it? Let's do the correction. So this will be xn, x naught, everywhere. Let's check if it is everywhere or not everywhere. This is correct. Here is correct. Next one. Let's go first. xn minus x naught, xn minus x naught, xn minus x naught. So these things happen, but if you pay attention, and xn minus x naught, so this is xn minus x naught, and this is, we can change it, so you can write it now. This is again xn minus x naught divided by xn minus x naught. And of course this is belonging to the sphere n minus 1. That means the Vn has the norm equals 1. So what we can say? By compactness of Sn minus 1, we can assume, we can choose a sequence, a convergent subsequence Vnk convergent to V0, of course, also is in Sn minus 1. N minus 1. So we get that d f x naught on V0 is equal to limit as n goes to infinity d f x naught Vnk, which is equal to 0. That's here. And that implies, so V0 belongs to the kernel of df of x naught, and that is a contradiction, because if kernel is non-trivial, then it cannot be surjective by the rank theorem. So x naught is not a regular point. So we got this statement. It's not a regular point. Very good. So now we are in the position. Now we are in position to show, to prove the main result, namely, and then we will explain how this result is used in practice. So theorem. Let f omega be an admissible pair such that f is C infinity map and 0 is a regular value of f in omega bar. 10, we have that the set inverse image, and put here like this, omega, is finite. We were discussing it earlier. So this is the set of all, put it like this, M, of all regular points in the image of 0, and we have that the degree of f in omega is equal to sum. So remember, I'm referring it to this particular set. So this will be k is equal 1 to n, and this will be signum, determinant, and this is derivative of f at the point xk. So we know that all those points are regular, so this is a matrix, invertible matrix. So you take determinant and you get the sign, so you basically determine to which component, connected component of the general linear group this particular linear isomorphism belongs. So this is our statement, and this theorem has practical connotations. Namely, let me make a first just simple remark before we continue. It means remark. That's a practical value of the analytic formula. This is called the analytic formula. Let's call this one analytic formula for degree. And I give here 2 stars. Practical value of the analytic formula. So notice that in practice, in order to compute degree of any arbitrary admissible pair, one should first find a regular approximation and then F0 omega of F omega, and second use the analytic formula. Of course, some homotopy arguments could also be carried on. We will be illustrating with several examples how this particular technique can be used, and the formations do not need to be small, it can be even large. So that means in such a case, this degree by approximation, by the, let's say, by the continuity property of the degree will be the same as this one. And 10, we have here analytic formula here, which is computable. So you have to solve the equation, which is supposed to be much simpler than the original equation, and get the values of the regular points in omega from the inverse image of 0, and then you can have the degree computed. So that's how it is. So let me begin the proof. So we start with the following. So since we have here that this is a regular value, so we have here that the set for each point maybe like this, for each point xk belonging to this set x1, x2, xn, m, and that one is equal f of minus 1, 0 in omega, we can find delta k larger than 0, and this is C lemma, And if you are not sure which one, so let me show you this lemma. So this is the lemma that we were just proving. So this lemma. So there exists a delta. Such that this is an admissible homotopy. So there exists a delta. So let's do it. Because lemma such that I have here admissible homotopy HK, and this is Tx, which is equal, and formulated 1 minus T, 1 minus T, and this is f of x, and this is plus T, and this is df of x k, and this one is x minus xk is b delta k xk admissible homotopy. Just to make sure that we have not too many. So actually, we can assume that, so we can choose maybe. We can choose delta is equal to the minimum of all those deltas, and this will in a certain way simplify our notations. So we can choose delta is equal like this and that. So and all this, all the homotopies h, k, tx or b delta k x k admissible for all maybe like I should not write like that because it's not correct. We should be very careful. And for all k case, the homotopy, now that's correct, homotopies h, and this will be k tx are b delta xk admissible. Okay, so that's our preparation. So let's go to the next page, and in the next page let's illustrate what is happening. The situation can be illustrated by this picture. So this is my omega. This is my omega. Then I have here the points. So this is my x1, this is my x2, this is my x3, and that's my last one, xm. And now we choose delta. So we have here small neighborhood. So this is my omega 1, so put it like this, omega k is equal b delta, maybe I should not write here, I should write here, omega k is equal b delta xk. So we have another one, so this will be like omega 2, so that's by the definition. 2, this will be omega 3, and this will be the last one, omega n. So notice the set, the red set, is the set of inverse image. So f minus 1 of 0, intersection omega is exactly the red one. So this is x1, x2, x. So what is the meaning of it? That means the following, that if I take if you take f minus 1 of 0 intersection omega, this will be contained in the union k is equal to 1 to n, and those are these disk balls. So I put here like this, instead of writing now, I'll just simply write down omega k. This is my omega k. So that means I have it. So like, moreover, by taking delta sufficiently small, we can assure that omega I intersection omega j is empty for I different than j. And then we can use next, we use the properties of degree. So let's use this property. Namely, we have here degree of f and omega. So that one is equal to, by the above property, so this is by additivity. So this is P1. So this one is equal, no, maybe like this. I think it was by excision. So let's call it excision. Excision. Okay, to be more precise, this will be the degree of f, and this will be union k is equal to 1 to m, and this is omega k. Then the next one is additivity. So it will be equal sigma, and this is k is equal to 1 to m, and then that one will be equal to degree of f, and this will be omega k. Then this one is by the homotopy, because we have here homotopy, so we can replace f by each of those homotopies. So let me write it down. So this will be the same as, put it like this, homotopy k is equal to 1 to m, this is degree, and I put here hk, I can put here t, put here small dot, that means for fixed t, for all of them is the same. So that will be like this, and again, what we are interested is in the, for the k, t is equal to, for t is equal to 1, so for, maybe I write it down, so for t equals 1, t is equal to 1, we are getting here that this is sigma, and that one is k is equal to 1 to n, and this is the degree. And remember, what is this hk of t1? Okay, so that's actually df xk, and this will be x minus xk. So let me change the x to the dot. So this is my dot, and then you have here minus, and that one is equal to xk, and this is on omega k. And again by homotopy, so this one is equal by homotopy, again homotopy. So I put here additional homotopy. I just put it like that, so this will be equal. This is k is equal 1 to n. This is the degree, and this is df of x. No, it's not by homotopy. So first we need to do by excision again. Excision. And I can take simply like that. This is sum k is equal 1 to n, and that one is degree, and this is df of xk dot minus xk, and I change that one to the ball sufficiently large. I will specify what it is. So what is r? R I put here like this is larger. So it's larger than maximum of xk. K is equal 1 to n. So there's only one solution. It's linear. That mark has only one zero. No, so there are no zeros on the boundaries. Now, again by homotopy. So let's do the homotopy. And the homotopy looks like that. K is equal 1 to m, and this is the degree. df, this is xk, and now we put here x minus, and the homotopy will be defined. This is our t belongs to 0, 1, so it's here. I put here t. That's my homotopy. This will be xk on br 0. So now again take t is equal to 0. So what do I get? This one is equal. Go down. Equal sigma k is equal 1 to n degree df of xk, and now that one becomes 0, so just simply this one without shifting. And now we have the formula that this degree, if the determinant of the derivative is positive, so it will be 1. If the determinant of this derivative is negative, so it will be negative 1. So we can rewrite it down. So I don't need this. And this will be sigma k is equal 1 to n, and this will be signum determinant, and this is df of xk, and we proved this result. The result is proved. The result is proved. Now, let us maybe finish here. It is actually a good time to finish, and we will continue at another let's say lecture. It will be, we'll be covering the next topic, so it's convenient for me to stop here. So thank you.